All right. So today's content is going to go over spontaneity and reactions when we're looking at a new thermodynamic quantity for us, which is Gibbs free energy. G is how it'll be symbolized. So we'll have that. That'll actually end this chapter on thermodynamics. Our test is on Thursday. It does not include any material from thermodynamics. That will be on exam 3. So the 2 topics that'll be on exam 3 are going to be equilibrium to some extent, but electrochemistry and thermodynamics, and a little bit of nuclear, not much. The content that'll predominantly be on exam 2 is all based around equilibrium, and equilibrium as applied to both reactions, solubility, and acids and bases. So exam 2, there's more than enough there for us to have a good exam on. So this content is going to be on exam 3. Still, with the way that the class is being offered and us being in week 7, it's important that we are able to go through this material now as opposed to actually going into week 8. I've lost track. At any rate, there's plenty for us to have on this one test. So we're going to have enough time to go into future stuff. So let me get into the content for today. And then start moving on from there. So I'll start to share my screen. Minimize this. So class today, 2046. So we're going through Gibbs free energy, spontaneity as it relates to that, whether or not a reaction will go forward on its own, non-standard states and standard states for calculating things like spontaneity, and then connections with Q and K, which are equilibrium. Equilibrium as a concept is probably one of the most important concepts in chemistry, meaning that reactions and systems tend towards equilibrium, but not towards a completion. And then, of course, the upcoming stuff is we have our exam on Thursday. That's the second of our exams. There's no quiz on Thursday. You will have extra credit due Friday and homework due Sunday. So all of those normal deadlines still apply to trying to get done. Now, let me move on to the content that we're doing for today. Jacob's joining us. You're doing good. Okay, so let me move on to the content for today. So Gibbs free energy. This is a new thermodynamic quantity for us. So far, we know entropy and we know enthalpy. Enthalpy being the amount of energy or heat that is sort of put into a process, a system, or surroundings. We know entropy, which is how organized or disorganized systems or surroundings are. So what is Gibbs free energy? We're going to start with the derivation. So the delta S of the universe is equal to the change in the entropy of the system and the change in entropy of the surroundings. And if the process that we're looking at is going to be spontaneous, that must be greater than 0, the sum of those two. Unlike other things where certain things are held constant, like heat and energy and stuff like that, entropy is always increasing. So the delta S of the universe is equal to delta S minus H over T. And all we did there is we substituted in the delta S of surroundings is equal to the negative delta H of the system over T. So this is something we came across in our last class. So if we recognize this and we substitute in there, we end up getting this expression. And I'm just going to multiply everything here by negative T. Okay, so everything's got a negative T multiplied by it. What that's going to do is cancel out the 2 T's that are right here. So what I'm left with is negative T delta S is equal to delta H minus T delta S. But this is delta S of the universe. This is delta S of the system. And this new thermodynamic quantity right here, delta G, is equal to negative T delta S. Plug that in for that right there, and I'm left with this new expression, delta G is equal to delta H minus T delta S. And this is the expression we use to determine the Gibbs free energy of something. And this may not mean a lot to you now, although it is relatively handy. But let's think about this. If the delta S of the universe is increasing because we have a spontaneous process, that means that multiplying this positive number by a negative number will give us a negative number. So if this delta G is negative, that means that we're dealing with a spontaneous process. If the entropy of the universe is not increasing, this is a negative number. Multiplying that by a negative number will give us a positive number, meaning that this process we're talking about is not spontaneous. Okay? So what is Gibbs free energy? Well, it refers to chemical potential and the ability to do work. And if delta G is less than 0, the process we're talking about is spontaneous, as I mentioned previously. And if it's greater than 0, it's non-spontaneous. And we're going to get to this later, but the system is at equilibrium when the delta G of that reaction is at 0, meaning that the reaction is not leaving its equilibrium spot. So we can calculate these things in a few different ways. We're going to look at it conceptually first in 4 different cases, and then we're going to look at it in terms of actual numbers. But let's look at it in terms of its cases first. So I've got this delta G equals delta H minus 2 delta S. And let's say I've got an exothermic reaction, so heat is being released. Okay, so delta H is less than 0. Because remember, if delta H is less than 0, then delta H is a product, that heat's a product, and we're increasing entropy. This was something, let's say, like something is exploding. All right, so this is less than 0, so this is a negative number. This is greater than 0. So that means that some positive number here multiplied by this number here. So a negative number minus a negative number is going to make, sorry, this negative number minus a positive number is going to make this negative. So this process is spontaneous at all temperatures, meaning that no matter what the temperature is, the value I'm going to get here is always going to be less than 0. So I'm not, again, this number here is negative, it's less than 0. S is positive. Temperature is positive because it's in Kelvin, so it's somewhere between 0 and whatever. So it's always a positive number. So a negative number minus a positive number will always be negative. So that means that this will be negative across all temperatures. An example of that would be this reaction here. 2NO goes to nitrogen plus oxygen. This is the delta H that's given off for this. And at any temperature, this will be a spontaneous process. Okay. Now, this second case over here, again, same exact reaction. Let's say I'm doing something endothermic, not exothermic. So if it's endothermic, my delta H is a positive number. This number right here is positive. And let's say that there's a decrease in entropy, meaning that this is a negative number. Okay? So now I've got a positive number minus a negative number, which is like adding a positive. And that means that no matter what the temperature is, this process will be non-spontaneous because this will always be a positive number. So something that is requiring heat and ends up more organized than it started will never be spontaneous at any temperature. An example of that would be oxygen turning into ozone. Okay? This is an endothermic process, requires 285 kilojoules of heat, and I have 3 molecules becoming 2 molecules. So at any temperature, this will be a non-spontaneous process. Energy will need to be put into the system in order for this to happen. Another case, let's say I've got an exothermic reaction, so heat is being released. And I am decreasing entropy, that is, I'm giving off energy in terms of heat, but I'm ending up with something that is more organized. So this number here is negative. This number here is positive. So this process is spontaneous only at low temperatures. This is an example of something like that. So I've got my H2O going to H2O liquid going to H2O solid. This is something that will end up requiring it ends up being more ordered. A solid is more ordered than a liquid. And so my delta H for that ends up being negative. And so my delta G for this will end up being negative, but only if the temperatures are low. And this is a process that only happens when temperatures are low, liquids turning into solids. Now here's another example. I've got an endothermic reaction here, and I'm increasing entropy. So this ends up being a positive number. So this is positive, and this is positive. So a positive minus a positive, that could be negative, but only if the temperatures are high enough. So if the temperatures are high enough, then it's a spontaneous process. An example of that would be evaporation, a liquid becoming a gas. So I can change here. So if that's the case, liquid going to a gas, this takes a certain amount of heat. Yeah, that's why you sweat. You give heat to liquid that's turning into a gas to then ends up cooling you down. But only at high enough temperatures will this end up occurring. So just to summarize, there's this table here, 19.1 comes right out of your text. So at low temperature, so if the first example here is spontaneous, delta G, high temperature, spontaneous, delta G. So I've got low temperatures, high temperatures. So if delta H is negative, delta S is positive, this is always spontaneous. If delta H is positive, delta S is negative, these are never spontaneous. If delta H is negative, delta S is negative, this is spontaneous at low temperatures, not spontaneous at high temperatures. The example there is condensation. And if delta H is positive, delta S is positive, then I've got something that is non-spontaneous at low temperatures and spontaneous at high temperatures. An example of that is evaporation, something going from a liquid to a gas. The cool thing about this particular equation, delta G is equal to delta H minus T delta S, is it does give us that temperature dependence based on things. So let's look at this process here. We've got a delta G that we'd like to calculate at 25 degrees, and we want to determine if this is spontaneous and what happens if the temperature increases. So I've got this molecule here, C2H4. It's going to absorb 2 more hydrogens and become C2H6. So I'm going to use my delta G being equal to delta H minus T delta S. And I'm given this information here, this delta H and delta S. So I can plug this in here, plug this in here. The only difference is, notice that this is in kilojoules, and this is in joules per Kelvin. So I either need to turn this into joules or this into kilojoules. And I've opted to turn this one into kilojoules. So I divide this by 1,000, turn it into kilojoules. So 137.5, negative 137.5, minus T delta S. Run that into my calculator, and I get negative 101.57. So this is spontaneous because this is a negative number. Okay, spontaneous. However, what if my temperature increases? At higher temperatures, delta G becomes closer to 0 and becomes less spontaneous. Right? So if I started increasing this temperature, a negative number minus another negative number, this negative thing keeps on getting larger. Eventually, a number minus another negative number is like a positive. This will eventually cross the line and go into 0. So this stays spontaneous at low temperatures. At high temperatures, it is no longer spontaneous. And that is just like this one right here. Negative, negative. Any questions on that one? If you want to unmute yourself or put it in the chat. The math itself is not that hard. It's just a matter of realizing what's being asked. Okay, we'll move on. So what we can do now, we looked at delta S's of various processes. We're going to look at the delta S of reaction at standard states. This little superscript of a degree sign is for what's known as standard states. So what are standard states? Well, a standard state for a gas is a pure gas at a pressure of 1 atmosphere. So if we're dealing with a gas at 1 atmosphere and it's the only gas around, pure, then that is a gas in its standard state. For liquids and solids, a pure substance at 1 atmosphere, so it's under a pressure of 1 atmosphere and whatever temperature we're dealing with. So liquids and solids don't really have atmospheres, pressures that we're worried about. but the environment that it's in needs to be at 1 atmosphere, and the temperature needs to be whatever it's specified as, which is almost always 25 degrees. And for a solution, we're talking about a substance that's in solution as a concentration of 1 mole. When those are the cases, we can use things in their standard states. So how do we get the standard entropy for a reaction? So what this is a change in the entropy for a process where all the reactants and products are in their standard states. So it just basically looks like this. The standard state of the products minus the standard state of the reactants will give us the standard state of the reaction. And the change in these things, so the change in the standard state of products, change in the standard state of the reactants, will give us the change in the standard state of the entropy for the reaction. And get used to seeing this products minus reactants stuff. It's what we're going to be doing a lot of in this portion of the chapter. But basically, if we know how things end up and we compare them to how they started, the difference between the two is their change. So this gives us what I think is one of the more interesting philosophical things that we can think about in the chemistry class here, which is the ending of the laws of thermodynamics. So there are two laws that you've been exposed to. The first is that the total internal energy of the universe is constant. There's no free lunch. The second is that the universe is tending towards disorder. That is, delta S of the universe is increasing. And now the third is that the entropy of a perfect crystal at absolute zero is zero. So absolute zero is 0 degrees Kelvin. It is the coldest anything can become. And at that temperature, there was only one way for a crystal to exist as a crystal. And so its W becomes 1. So if we use Boltzmann's equation, that becomes 0 by definition. All right. So if the temperature is 0, this leaves the equation. So when T is equal to 0, the amount of work that can be extracted from the system is equal to the amount of heat in that system. And that is the only time when there is a perfect exchange between work and heat. Okay. When this becomes 0 and this drops out, these two things are equal. At any temperature that is greater than 0, there is always a certain amount of entropy that we have to deal with, which means that the amount of heat that's in a system is not equal to the amount of work that can come from that system. So at any temperature above 0, some energy is always lost to entropy. The amount of chemical potential in the universe is always decreasing for any spontaneous process. So think about what this might mean. If you spend any time or energy cleaning, what that means is you're using some heat and converting it into work and putting things back where they go. It's your attempt to overcome entropy. And it's a futile attempt. Entropy will always win. And so when I had idiot roommates back in college, I would say things like, hey guys, clean up. And like my smart ass roommate would say, I'm not contributing to the heat death of the universe. The heat death of the universe is this time when we can no longer turn heat into usable work. It's a funny answer at the time, but the place was. So you might remember that there are ways that we talk about the laws of thermodynamics that sound kind of colloquial, but they sum them up nicely. So the first law is you can't win, you can only break. Second law is that you can't break even unless you're at absolute 0. That's when our entropy drops down to 0. And so that kind of brings us down to the third law. There's a fourth unofficial law, which is that you can't get to absolute 0. This is an unachievable temperature for us. So this will never become a 0 situation. And so if I can't win, unless I'm at this very unachievable temperature, and that unachievable temperature is truly unachievable, then in terms of energy, the rule is you lose. You'll never be in a situation where you can get something for nothing. So, and that is a real concern. People, when they're trying to make things as efficient as possible, this equation right here is what they continually run up against. So they're always going to end up losing something to entropy. So there are some entropic trends. Entropy is one of those things, because we actually have a 0 state, a state at the lowest possible temperature, we can actually assign absolute values in entropy for all things because we have something to compare it to. We don't have that for enthalpy. We don't have that for Gibbs free energy. So gases have their own values of entropy. And typically, as gases get heavier, as their molecular masses go up, so do their entropy values. And this is a good example right here. If we go down the noble gases, helium is 126 and xenon is 169. Okay, so that's just for things that have a molecular mass that's associated with it. These are solids here. If you take a look at them, solids with two things in them or solids that have just one thing in them. How these numbers get assigned is beyond the scope of what we would go into in this class. But there's some other neat things to notice. So if two things have different masses, they don't necessarily follow the trend in terms of just mass. So argon has a mass of 39.94. It has an entropy of 154. Nitrogen monoxide has a molar mass of 30. It has an entropy of 210. And that is because there are two atoms in nitrogen monoxide. So there are lots of different ways that it can be arranged in space. Whereas argon, you can think of as just a sphere. There's only one way that it can be arranged in space. And only a certain number of things that it can do. It can't vibrate in and out, where like these guys can, so there can be vibration in this direction. It can twist and turn rotationally. It can translate, that is, move around. Whereas argon, rotation, yes, it can rotate, but it's always on one axis. It does not vibrate in a way that we can see it. These two molecules here, they have pretty much the same molecular mass. Carbon monoxide, there's only two atoms in it. It's linear, so it's got a relatively low entropy. C2H4 ethane, that has 6 atoms in it, and each one, the carbons at least, they are arranged in such a way that they are tetrahedral. And because we have those two tetrahedral things there, it makes it a more complex way of arranging things. So we have a higher value of this. There's more ways that it can be, arranged. So, but even though it's a more complex thing, more atoms means more disorder. So let's calculate the standard entropy change for a reaction. So the way that we do that is we look at the standard entropies for the reactants multiplied by their coefficients, and we take away these standard entropies from the products. So we have the products minus the reactants again. So I'm reading this backwards. Subtract the standard entropy of the reactants multiplied by their coefficients from the standard entropies of the products multiplied by their coefficients. And stoichiometric coefficients are these things, NP. You'll see it, it's pretty straightforward when you see it in a real example, which is what we're going to do next. These Greek capital sigmas here represent summations. So we're going to sum these things over the number of things that are in it. And then we get this delta S of reaction out. So let's do this for a balanced chemical reaction, this one. So I've got 2H2S plus 3O2 goes to 2H2O and 2SO2. Now just looking at this, I've got 5 molecules, a fairly disorganized system, becoming 4 molecules. This is more organized. So if I had to guess, this would probably be a non-spontaneous process, meaning that I should have a delta S that I believe is negative for this reaction. But let's see. So this is the formula that I end up using. The stoichiometric coefficients for my products, so this 2 and this 2, times the delta S of my product, so whatever the delta S is for this, whatever the delta S is for that, minus 2 times whatever the delta S is for this, and 3 times whatever the delta S is for that. Well, where do I get those delta S's? I made a table, but as I've mentioned lots of times, last semester and this semester, there are advantages to having the physical textbook, and this is one of them. If you have the physical textbook, back to the end in the appendix, and I believe it's appendix 2, there are tables, large tables of thermochemical information, and that's where these numbers come from. What you can see here is there's like a substance like potassium hydroxide here, and there's delta H, there's delta G, and then there's just S, entropy. And we can look up those numbers. And so all I would need to do is say, okay, I want the S for water. I'd actually look up the way it's organized here. I'd look up oxygen. It's a hydride of oxygen. And I would find this number. The phase of matter matters. So if they have H2O liquid and H2O gas, this reaction specifies gas, so we want to make sure that that's the number that we put here. So when I made this table, that's where I made it from. I got all those numbers from that portion of the book. And if we were doing this class face-to-face, I would have photocopied this for you and handed it out so that you guys would get used to looking these things up in tables. Okay, and it's just what we do. So we do that for each one. So the two products here, water and SO2, these are what they come out to. O2 and H2S, these are what these come out to. So when I arrange them, 2 times water, which is this one, plus 2 times sulfur dioxide, which is this one, minus 2 times H2S, which is this one, and 3 times 205.2 oxygen, which is this one. So it's the sum of these two minus the sum of these two. Literally what it says up here in this equation. The sum of these and the sum of these, and these 2's here, they come from the stoichiometric coefficients here and here. So I've got 2 moles of water in my reaction, so I need to multiply this by 2. So I go through and I get the answer, and I get negative 153.2 joules per mole Kelvin. That makes sense because I've got 5 molecules becoming 4 molecules. Okay? So you'll want to spend some time with some of these things like that. It's not a very hard thing to do. It's just a matter of wrapping your mind around the question that's being asked. We'll pause here for any questions. Is there anything you guys want to ask about this one? Okay. Let's move on. So if we can do that for entropy, we can also do that for delta G. So there are 2 ways that we can do this for delta G. I'm going to show you both ways with the same reaction. One is using this delta G minus delta H minus T delta S. It's one way. And the other is to use a table of values from delta G, which might be easier, might not, depends on the information that you're given. Our goal is to determine the spontaneity of a chemical reaction or process. So in this one here, this is, in terms of entropy, a non-spontaneous process, all other things being equal. However, this is a reaction that actually might occur. Let's say if it's exothermic and I've got a negative delta H. If it's happening at a low enough temperature, this might actually go forward. So that's my main goal here. Delta G ultimately is the arbiter of whether or not something is spontaneous or non-spontaneous, which is the reason that exists. Do we have more chemical potential or less? So we're starting. So SO2 plus half a mole of O2 goes to make SO3. This is a balanced chemical reaction. Typically, we don't see fractions here as coefficients, but it is fine because we want to see 1 mole of this and 1 mole of that. And fractional coefficients, they are, despite what we tell you in Gen Chem, they are left. So we're going to calculate this at 25 degrees C and determine whether or not it's spontaneous. So what I did is, again, went into the book and I looked up delta S, and this shouldn't be a delta. Sorry, the delta H and S, this should not be a delta S. That delta should be gone, so I can get rid of the delta here. So in the book, this came up. The nice thing is, for pure elements like oxygen, O2, N2, solids, certain kinds of solids at least, the delta H for those is always 0. An element by itself, its pure state is delta H 0. Okay, so what I can do is I can use this information to figure out what the delta H of reaction is and the delta S of reaction. So if I'm going to do the delta H of reaction, it's this negative 397 minus some of these 2 things here. Also, I'm going to change that to match. So when I put this in my calculator, this is the number we come up with, 98. If I do the same thing for delta S, 256, which is what this one is right here, minus the sum of these two times the stoichiometric coefficient. So 248 plus half of 205.2, I get negative 94 joules per mole. So I can plug that into my delta G minus T delta S. So here's my delta H, 98, I figured out there, minus T delta S, which is this. I converted this to kilojoules. Okay. And here's what I come out with, negative 70.9 kilojoules per mole. So my delta G is negative. This is a spontaneous process. If I were to raise this temperature, however, even by just a little bit, it would no longer be spontaneous. And that's because I've crossed the threshold and this becomes 0 or higher. If that becomes 0 or higher, it's no longer spontaneous. Now, from tabulated values, it's the same thing. We'll get to the same answer, just a different way. And this works the same way as the delta S. Whatever our numerical coefficients and thing are for our products, minus whatever the numerical coefficients for our stoichiometric amounts are in our reactants, subtracting one from the other, subtracting this one from that one, will give me the change in the reaction. So again, you can look these up in a book. Pure substances like hydrogen, oxygen, nitrogen, they all have a delta G of 0. Graphite also. Diamond does not have a delta G of 0. It has a little bit of chemical potential in it. And then we see different numbers for different substances. So how do I calculate this at 25 degrees Celsius and determine whether or not it's spontaneous? Using those delta Gs. So I looked up in the book the values of delta G for these two. Again, for oxygen, it comes out to 0. I plug it in, so negative 371.1 minus negative 300, and that comes out to negative 71. If you remember, the answer we got from the previous one was negative 70.9, which is basically negative 71. So the answer is the same. You can do this in one of two ways. This one's a little less work. Sometimes you have this information, sometimes you don't. Sometimes you can use this, and if you don't have the information, you can not use that. But how free is this free energy? What does it actually mean? This was something I found confusing as an undergrad. And even later in life, I occasionally still find confusing. But it does work like this. You have a battery, and you are pulling energy from that battery to do work. Like this motor here will turn, and it's going to do work. That's kind of how we envision a lot of things working. Like your cars do this. Electric cars do exactly this. And then if you run this motor in reverse, it generates current that can go back into this battery. So that's exactly how electric cars work. When you're braking, they'll run the motor in reverse so it can generate electricity to go back into the battery. It is not a free exchange in both directions. Because in both directions, we're moving current through a wire. As that current goes through a wire, we end up losing a little bit of energy in the form of heat. And we can calculate the amount of energy that's lost, and that ends up being part of this thing here. So the amount of heat that we have being converted into work, these are only equal to each other when T is 0. We can never get to T being equal to 0. So for every process, every real process that uses something like this, and batteries and motors are just one example, we are always losing a little bit of energy in the form of heat. That ends up heating the surroundings and gets dissipated. So energy, I always say like energy is always constant. That is true. However, energy is always being transformed into something less useful. And so when we say like, we're running out of energy for something, there's still energy in the battery in your phone when you're at 0%. It's just less useful. You don't have enough to actually run the circuits that you're in. So when your battery is dead, you need to plug it back into the wall, and you might notice that your phone might feel a little warm. Same thing if your phone's using, running some program and using a lot of current, it feels a little warm. Okay, and that's because energy is being lost to heat. So This gives free energy. It doesn't mean that it's just free and available. It's the amount of energy that we're able to turn into some kind of work from heat. And it's the conversion of heat into work that we're really interested in. For those of you soon to be engineers, you chemical engineers and so on, this is an important process. You're going to look at something called Carnot engines and Carnot cycles so that you can learn more about this. And then go work for Tesla and make lots of money. So let's look at free energy under non-standard conditions. This is another form of a reaction I'd really like you to pay attention to. I've got it here in red. The delta G of a reaction is equal to the delta G at the standard state, 1 atmosphere, 25 degrees Celsius, when everything's in a standard state, plus this little RT ln Q. So R times T, R being 8.314 joules per mole Kelvin, T being whatever temperature we are in Kelvin, natural log of the reaction quotient Q, which is how far we are away from equilibrium. So if I've got liquid turning into a gas, my delta G for that is not below 0. This is a positive number. Now that's weird because I am pretty positive that water evaporates pretty easily. Okay, so what's going on here? Well, this is at standard conditions, 1 atmosphere. And I never really have 1 atmosphere of water. So the partial pressure of water is much closer to something like 0.0313. So we're going to go into the next slide. And so if I'm saying under standard conditions that I've got 1 atmosphere of water, natural log of 1 is 0. So this term becomes 0. So the delta G of this reaction is equal to the delta G of it at its standard states, which is 8.59. That's a positive number, and it's telling me that water doesn't evaporate. Not true. Same process here. At equilibrium at 25 degrees Celsius, when the partial pressure of water is not 1 atmosphere, which is what is assumed in a standard state, but considerably lower, 0.03, okay, so like, what, 3% or so, atmospheres, then that's what its Q is. So if I was to write a Q expression for this, liquids don't appear in those. So there's my Q. So delta G reaction is equal to delta G reaction plus RT natural log of this number, which is not 1. And this becomes negative 8.59. These two numbers cancel out, and this becomes 0. The delta G of this reaction at 25 degrees Celsius, when this is the partial pressure of water, tells me my delta G is 0. So I know what happens when it's positive. It's not spontaneous. When it's negative, it is spontaneous, so it moves forward. At 0, what does it do? Nothing. At equilibrium, delta G is 0, meaning that it has no potential to move away from equilibrium. All reactions tend towards equilibrium and not away from it. So what a lot of people tend to think of is like, I'm going down this, I'll swing through equilibrium, and then I'll go back up this way, and I'll go back and forth until I come to rest. No, when I get to equilibrium, unless I'm being pushed, someone puts energy or more stuff into the system, it stays here. So equilibrium can be approached from either side, but we don't go through it like it's a pendulum. That doesn't happen. So let's consider this reaction. We've got H2S, that rotten egg smell, plus SO2, also pretty smelly, goes to make sulfur and water. And the delta G of this reaction is negative 102 kilojoules. And that really should be delta G at standard states. Okay, so what does it look like under these conditions? 2 atmospheres of this, 1.5 atmospheres of this, and H2O's atmosphere is this. Okay, well, there's some things that need to happen. One is I need to figure out what my reaction quotient is. So it's just products over reactants. Notice that the sulfur is not a part of it. It's a solid. Solids do not contribute to my reaction quotients or my equilibrium constants. So this divided by 2 squared divided by 1.5 raised to the 1. This comes out to 1.67 times 10 to the minus 7. So that's my reaction quotient. It's a small one. Whether or not that's bigger than K, I don't know, because I'm not given a K. How do I get my delta G of formation? So I was able to go in the table and look these things up so I can calculate it. It's my delta G naught is negative 90.3. Okay. So my negative 90.3 plus this, I can calculate this out to be negative 129. Okay, so under these normal conditions, or under these conditions where my pressure of this is 2, pressure of this is 1.5, pressure of this is 0.01, I have a spontaneous reaction. And what that tells me is that this is a negative number spontaneous, so my reaction should be going in this direction, forward. H2O should be continued to being made. So that means that over time, this partial will go up, these partials will go down until I get to a delta G of reaction of 0. The relationship between that and K, remember at equilibrium, the delta G of reaction is 0. So if I plug that in here, then this expression becomes delta G of reaction equals negative RT natural log of K. Your book goes about it this way. I found it a little confusing when I read it. I'm not sure if I can make it much more clear, but the idea is, let's say that you have these reactions here and you know their K values. They're either less than 1, more than 1, or equal to 1. So if your K is less than 1 and you're given a Q that is equal to 1, okay, that means that you're on the right-hand side of this expression. That is basically you have too much going on in the product side. So this will end up being spontaneous in the backwards direction. So your delta G here would be positive. And this one right here, if my K is greater than 1, my Q is only equal to 1. That means that I've got too much too much reactant, not enough product. And so that means that the forward reaction is spontaneous. And here, if my K is equal to 1 and my Q is equal to 1, that means I'm at equilibrium, so my delta G should be 0. So right here, this would apply. There is a temperature dependence on it. Your book points this out, and you can plot this. We're not doing anything with this, math or otherwise, but it is something that you can plug numbers into and get. But it's something that I really wanted to point out, because we start with this expression, delta G is equal to negative RT ln K. You might do some fancy substitutions. Your book does go through what those substitutions are. You can turn that expression into this, which is a y equals mx plus b. So the slope of this line, would be, here's your x, your 1 over temperature, and the slope of this line would be the negative of your delta H of reaction R. So one of the things that we know is that if I have the delta H of reaction, this is a negative number. The opposite of that makes this positive. If I increase this temperature, I'm going to end up changing my K. So let's say if I increase the temperature on an exothermic reaction, I end up, driving it back towards the reactant side, which means that my K should get smaller. And the opposite is true if this is an endothermic reaction, where delta H is positive, and I increase my temperature, that's increasing one of the reactants, so things would shift over to the product side, and my K should get larger. So K is dependent upon temperature, and it's something we alluded to back when we were looking at K constants, but here you can actually do the math and figure out the degree to which that is true. However, because H is temperature dependent and S is temperature dependent, the range in which this is a linear relationship is very small. Going outside of that range, the math gets much more challenging because these are no longer constants, these become expressions outside of the scope of this class, so you do not need to worry about that. And if I just have a 2-point version here, this is how I would go through and do it. Again, a little fancy math to get to this spot, but this should look very similar to something we saw in the first or second week class, where we are doing the 2-point version of delta H's for various temperatures. That is that. stop my screen share. Now, clear as mud, right? It's worth reading. Your book does give you some good information to go on. If you can wrap your mind around a couple of simple ideas, you can make things a lot easier for yourself. For example, if delta G is a negative number, you have a spontaneous process, no matter what's going on with entropy or what's going on with enthalpy. If delta G is a positive number, it's a non-spontaneous process, no matter what's going on in those other two things. If delta G is being calculated without using standard states, one atmosphere and other stuff, you've got that little correction value with RT element or K. That's what we're doing. So if you can simplify these big ideas to just a couple of easy statements, it helps a lot for you to kind of understand what you're even trying to figure out. And if you really have to condense it down to just a single idea, it's how much work can I get for how much heat? If I got this much heat that can come out of a reaction, how much work can I expect? And that is what delta G tells us. Thermodynamics as a study is one of these things that was sort of developed because we started developing engines and we needed a way to make sure that they were efficient. And we came to a lot of these understandings out of that process. So a lot of this stuff came to us during the industrial revolution. It's neat. As far as science goes, that's kind of recent. So that is the last of the material that we're covering for this week. So on Wednesday, when we have class, what I'm going to do is I will do some review problems. I will put some up there that I think are representative of what you can expect on the exam. And if you have questions that you want to go over as part of your preparation for the exam or things on the exam, please let me know. Email me and tell me. That way I can make sure that I've got them in there. You can even request specific ones out of the book or quizzes or anything. When the test becomes available, things that prepare you for the test will not be available. So exam 2 prep will stop being available once the new test gets posted. That is pretty much it. So if you guys have any questions, let me know. I'll be putting up your grades for last week's homework and extra credit probably later on today, maybe early tomorrow. It should be good. Any questions? Things you want to go over? All right, then. I will see you guys on Wednesday. All right? Good luck with everything.